Good morning, everybody. My name is Riaan from Johnson Wagner. So I'm gonna be chatting about using geophysics to fill in gaps where we don't really know what's going on in terms of that straw in the ball thing. So I found it very useful in the past investigations that I've conducted. So based on the discussions of this presentation, we're just going to give a quick introduction and talk about a bit of applications, and then just go into some case studies, but not really throughout go into detail and everything, but just highlighting the geophysics, and then have some concluding remarks. So geotech engineering is often referred to as a dark art of engineering. Well, I think geophysics is a bit darker because you use waves and currents to give us physical properties of rock and soil. So I think that is a bit darker. So geophysics is a good at measuring differences. It's all about turning invisible subsurface information into usable, visible, and often highly accurate pictures. The geophysics complements the engineering geology, and it is a very useful tool in the belt of anybody doing a geotech investigation. So how are we applying these geophysical methods? I'm looking mostly at the TSF applications, but this can be applied to anything where we're doing geophysics, geotech investigations for. So we normally start off with a desk study phase, and although the geophysics is it's a site-based exercise, it's useful to combine it with a desk study phase. So during the desk study phase, we usually do a lot of aerial photo interpretations, and with this, we can identify any features and like faults and geological contacts or areas of interest that we want to target with as the investigation progresses. So these are useful to pick to further investigate these features that are identified. It also gives us an initial view of the subsurface conditions. So just if there's existing information available and you combine that with the geophysics, then you already, without digging a test pit, without drilling a bore, you already have some sort of idea of what's going on. And then further on, if you identify any features, you will be able to get the geometric layout of these features. And you know how to investigate and how to approach these. So the second application is also refining the drilling program. So this is now the second step in it. So if you have an idea of where those features are, you can do more targeted drilling. So you get more bang for your buck. You don't want to be in a situation where you drill just on a grid, for instance, for a new facility. You drill on a grid and you come back and you do test pits and you find out, oh, yes, this is a major feature just running 10 meters away from where I actually drill. So it is useful in terms of that, getting more information out of the limited budgets that we sometimes have on these geotech investigations. Also, the main important thing is it assists with helping the orientation of and the positioning of the ball. So if we pick up a feature that's dipping at a 30-degree angle and it's striking, well, you can't really determine a strike, but you can effectively use that to position your ball so that you intersect the features that was identified at a depth where you don't encounter the upper weathered material, so that you actually encounter it at a depth where you can get really good information in terms of getting shear strength parameters, see how the rock is actually, is there infill in the joints, is there weathering along the dikes, and all of that. So that's a really good idea, application for it. The second is the investigation of embankment composition. So with a lot of these old facilities, there's very limited information on it. So if you are using this geophysics as an example, as a method to investigate how the embankments was constructed, you can get a really good idea of what the quality of the material was, what was the quality control that was used during the construction, and yeah, just get a feel for the embankment in the facility. So yeah, as I said, with many of the existing informations, the exact methodology of the embankment that was constructed is unknown. Similar to if some contractors will say, "Oh no, we did center line a construction and we raised it like this," but after drilling, and there's like, yeah, it wasn't really a center line. So this really helps with just identifying those pitfalls. And then the other good application is the investigation of the groundwater conditions. So it can be used to map the phreatic surface. As Adrian showed yesterday, you don't want the water table to be intersecting where the outside of your toes. So this can be done. You can run the geophysics lines along the embankments, or you can run it up the embankments along the benches, but you just have to be careful where you position your stations so that you account for that irregularity in the topography. So I just want to go into a first this study. So this was one of those old facilities that was it's dormant at this stage, and I'm no longer depositing on it, but we were tasked to do the investigation with to get this GISTM compliant. So first of all, we did this study, and we also combined this study with geological mapping and the geophysics survey. So because we're thinking that because there's very limited information, we can get a lot of valuable information from the mapping and the geophysics. So during the mapping, we identified really, there's a lot, I must say, this was a really geologically complex area. I mean, there's a lot of stuff that I haven't included. It's not really applicable to geophysics, but these are the prominent features that we've identified that might be affecting the stability of the TSF. So we identified these faults running that might be intersecting. We didn't really, we mapped them over here in these outcrops. This is the areas where they mined. We mapped them and we extrapolated just this is where the footprint or where they might intersect the facility. So based on this, we positioned our geophysics lines to try and identify if these features are in fact running below the facility and intersecting the embankments at really unfavorable areas. So as you can see, this fault was dipping in this direction, which is very unfavorable for this embankment. The entire area slopes from this way in this direction. So the deposition is also was done from there, and the water flow down, it pulled down here. So this is the results of the geophysics. So we did on each and every line we did ERT, and then we coupled in with MASW, especially the ones along the toe. We did MASW. Sections of it, the mine really didn't agree with our budget, so that's why we only targeted certain. Oh, I'm pointing at the wrong screen. We only targeted certain areas with the MASW on top of the crest. So if you look at this this area here, that's mostly the embankment material. So it's I think if you look at the resistivities, it's fairly low. So it did identify that there is a presence of water in it. I mean, some of the previous contractors that was on site, you could still see the places where they got stuck in it. So although this is a really old facility, there was still a lot of water in it. So that was the main aim of doing the facility, the resistivity along the crest of the facility. But the main thing that we picked up in this is these really prominent features that's running there, and that made me really excited because it means that it could be these faults that we're intersecting. So these arrows identify the places along the traverse where we intersected them. Well, they don't really match up. I mean, if you look at this, a lot of stuff can happen there. Faulting, displacement, strike slip, everything. So the features that we're intersecting here could not even be these one. It could be something else that's covered with sand that we don't even see. But in any case, we did pick up these massive features here. Another thing is these features are, if you look at the map and the scale there, it's about 40 meters wide. And as Bruce said, also straight lines doesn't really, I don't like, but I mean, the geophysics are so prominent here. We have to investigate it. We did, as part of this phase of the investigation, we did drill sonic drilling. We did do sonic drilling through the facility just to get an idea of the embankment material. So as a next phase, we are planning on doing more targeted drilling towards this and identifying these features. But the sheer width of this, just a second, the sheer width of this feature and just shows you that there's something big that's running down there. It could be that there's just a little bit of moisture content in this feature. It might be a combination of a lot of faults in creating like a shear zone where there's just a lot of water that gets recharged from the facility itself. So the geophysics could be actually painting a picture that's a lot worse than it actually is. And this is sort of the combined the conclusion we got from combining the ERT with MassW. So the feature that was done, the traversal was done along the toe of the facility. You have this feature here as well. But if you look at the MassW, what is that? That's roughly about where the 700 meters per second head is. So that's about the depth to what we anticipated as bedrock. And you don't really see at these changes these massive features that was picked up in the geophysics in the ERT survey. So that also just shows you that this might just be a very fractured rock zone, not necessarily very weathered, but still very much intact. So yeah, that was and you also picked it up along the western embankment, and the same feature here, low high shear wave velocities very close to surface compared to this ERT feature that was done here. So that's just a 3D representation of what the fault line, these features look like. So the stuff that we intersected is running in this direction here. The same over there. I've got another picture. This is a photo of just of those one of those features that we mapped. So you can see here, even from here, you have this multiple synthetic jointing or faulting that's complementary to this massive feature that's over here. So, and you can see the striations on that. You can see that there was definitely some movement on it. So the other thing is that I wanted to identify is we found out later on in the investigation, why was this buttress placed there? And after a lot of investigation and speaking to people, they said, no, there was some instabilities in the past. So, which also then further our anticipation that there's definitely features running along this facility here. So that's just the case study, the first case study. And the second one, it's also just sections of an ongoing investigation. It's just just shows you the power of geophysics to investigate the embankment composition. So I'm just highlighting this one particular embankment. So this is it's in between three compartments, but based on our desk study, it was I identified I went through a lot of all the historic images to try and see how this facility was built, or if there's any indication of what material that was used for the embankment construction. And this is an all, I think it was from it's early 20s, this image, but I just want to draw your attention to this section here that's just clouded by the cloud. There appears to be a gap in the embankment. And as far as I'm concerned, that's not really good for a tailings facility. And they also started depositing without having to complete it. Another thing that you can also see here is they've deposited, they keep on saying to us, no, they just used material from the pit. But here you can see that this is completely different to that. I mean, the quality control, just from the picture, you can see that there's a high variability in this. So that's also, and the main thing is like, when they completed this, hopefully, well, they did, if you look at that feature, did they remove the tailings before they completed this? So that was a key area that we wanted to investigate. So this is just the ERT and the MASW of that section. And here you can clearly see, and I saw that, got really excited. I was like, okay, yes, we picked up something here. But if you look at the MASW, although the MASW didn't really, they lost a bit of data there, but you can't see any dip in the material. Although this is very blue, it's 100, 200 meters per second. So it shows it's not sludge. It's actually, it's relatively, well, it's fill, but it's not tailings. So and you get these pockets of really poor compacted material in there. So that's just, I just want to showcase this exactly how we can pick up the differences in the embankment material itself. This also this is the first compartment that exactly drops down to the second compartment. So you can see the difference in the moisture content that was identified. This compartment is, the tailings level is a lot lower compared to that, which is most likely why there's a lot more seepage and a lot more water still in this facility. Although this is also a really old facility, it's still wet. There's a lot of trucks and stuff that can still get stuck in it. But the main thing is just to have a look at the complete difference between the two, the ERT and the MASW. And although they look very different, yes, they complement each other so much if you know where to look. And but this just the main thing about this geophysics, the survey is we had a lot of discussion with the geophysicists, and we told them that these are the certain things that we wanted to target. And I just want to highlight on, well, okay, on further investigation, we found out that there's a pipe that's running there, and then it goes underneath the access road, and then it goes down again, which is why we found that anomaly there, which is really sad. But I just want to show you how the level of information that we got. These intersections, that's the high resistivity or relatively high. These low resistivity zones correlate very well with these deposition points, where this would, I mean, the tailings would flow out here. So this areas would be a lot more, will have a higher moisture content to that. And although this facility is no longer active, you can still pick up the difference, the variation in the material itself. So just shows you how good the geophysics has become, and what level of information that we can get out of it. So, on conclusion, I just want to say, although geophysics seems expensive at first, it will save you and the client a lot of money in the long run. And you don't even have to wait until the design phase. You can still save a lot of money just from your drilling program, and the amount of investigation that you need to do. And in the second point is that to get the best out of the survey, both the geophysicist and the engineering geologist or the geotech engineer needs to know what are the limitations, the expected conditions, and the desired outcomes. So what does each party want and to conduct their work effectively. And then allowance needs to be made for reanalysis of the model. I think this previous survey, we did send it back. There was very little, because there was initially balls that was done along the edges of the facility, but very little. But we did reanalyze the data, and it actually improved the level of accuracy of the survey. And then the last point is geophysics is very effective at filling in the gaps between the data points. As we can see in all of these results, we wouldn't have been able to investigate it at that level without the geophysics. So that's my story.
Thank you, Riaan. Good. Time for one quick question from anyone? Yes, Wesley.
Thanks, Riaan. It's really cool to see how you're using the geophysics. I think just one quick comment on the MSW and ERI. I think MSW is not as sensitive to vertical features as electrical resistivity, so that might be why there's a bit of a decoupling of the anomalies. And obviously they're measuring different physical properties. So it could be that, or the other thing is the resolution of the surveys. They could be a bit off from one another. So I don't know if your electrode spacing was similar to the resolution from your MSW. We find that can also cause a decoupling of the anomalies. But very cool. Thank you.
No. Anyone? Oh. Two.
Thanks, Riaan. I have a similar comment to what I had yesterday about horizontal conductive zones being overestimated in inverse models. Those 40-meter wide vertical zones that you had in your inverse models, they might be only 10 meters wide or less.
Yeah.
They just appear much bigger in the, much wider in the inverse models.
In terms of from where we came from, we made it to minor where these are 40-meter wide features so that we can investigate them. So, but yeah, I agree with you.
Okay.
It is sometimes over-exaggerated.
Hi, great presentation. So I'm a student, so my question might sound stupid or what. So we are actually taught not to draw conclusions from one geophysical method, and I can clearly see use ERI and MASW there. So what happens when you get like two different results? Do you just drill, or you have to use another geophysical method?
You would always have to drill, I would say. If nothing speaks to each other, then you have to especially drill, because then you have to figure out what is causing these differences in the results. So yeah, there's nothing. These are just everything is tools that we use. Nothing can replace a actual profile in the ground, seeing what's going on below the facility. You can use that to extrapolate and get a high degree of confidence of what's going on, say 10, 15 meters away from the test pit, but you always have to drill or do testing.
Thanks, Riaan. One question. I'm interested to know, do you specify the station spacing for these surveys, or do you go with whoever's collecting the data?
We tell them, listen, this is the zone of influence that we're targeting, and then they provide the geophysicists provide their input on it.
You go with their recommendation.
Let's do this. And normally on some of the projects they've done test runs to see, listen, okay, let's do a test run and see what the quality of the data is. And then based on that, they upscale it and use it for the rest of the survey.
So what was the station spacing, if you can
I
remember
can't
it?
do- Can't really 100% remember what
Yeah.
this. It varied from embankment to embankment, because there's a lot of different things or features that we wanted to investigate.
But typically, what would it be? A range of 5 meters, 10 meters?
There's I know for some of it was 2.5 meters,
Wow.
on some of the just in that, especially in that area where we saw that gap in the facility. That was a really close spacing. But
So you vary it according to the
Yeah, yeah.
requirement.
yeah, it's very similar to if you do gravity surveys as well. You do it on a big grid, and if you find areas that might be of interest, then you increase the grid spacing on that as well.
Thank you.
So.
I think we're going to have to call it there. Do you mind asking him during lunchtime, just because it went longer? Okay, thank you very much. Awesome.